So our next speaker is Ken Vashaw from MIT. He's going to talk about the Connectedness Theorem and the Carlson Theorem for monoidal triangulated package.
Yeah, great. So thanks for the introduction. I'm very happy to be speaking here at this conference in honor of Dan Nakano. We started working together when I was a PhD student. We collaborated together, and I eventually asked him to be a second advisor on my thesis alongside Milan Yakimov. And so today I'm going to talk about some of the results of that ongoing collaboration. So I'll repeat a few things from Milan's talk just to remind ourselves. So one of the reasons I'm really happy to be giving this talk here is that it's very much inspired by the work of John Carlson from the 1980s, which he was doing here at University of Georgia. So this comes out of cohomological support for modular representation theory for finite groups. So here, the setting is G is a group whose order is divisible by P, K is a field of characteristic P. And the idea of a support variety is assigned to every finite dimensional module of G some particular closed subset of a topological space, which is proj of the cohomology ring, which we just heard a good bit about in the last talk. And so this allows us to use kind of geometric techniques on proj of the cohomology ring in order to study the representation theory of G. And just to remind exactly how this construction works, so here I'll denote I of A, the annihilator of this bimodule X to AA. This has some annihilator in cohomology ring. And the cohomological support variety of A is then just defined as, well, the closed subset of proj of the cohomology ring defined by this particular ideal. So those homogeneous prime ideals which contain the annihilator ideal I of A. And the big motivation for this talk is from this fantastic theorem from 1984 of John Carlson, which is that if you start with an indecomposable G module, then the cohomological support variety of A is a connected subset of proj of the cohomology ring. So I want to say another result, which on the face of it looks a little bit unrelated. So part of what I want to convince you of in this talk is that really these two different, kind of seemingly very different ideas are actually two instantiations of the same underlying phenomena. So, this second kind of seemingly unrelated result is that, well, if you start with some scheme X and it's a disconnected scheme, breaks down into X1 disjoint union with X2, we can consider this derived category of X, D of X. Then, okay, so this is not, this is a fairly straightforward formal result that this derived category of X breaks down as just a direct sum of triangulated categories into D of X1 plus D of X2. Or in particular, if you have some indecomposable object in D of X, then it really just corresponds to an object in the derived category of X1 or the derived category of X2. So, right, so the result on the previous slide, it's kind of a very deep, difficult to prove result. This result is kind of more formal and straightforward, but really, I want to convince you that these are two examples of the same thing happening in a more general framework. Okay, so this concludes kind of my motivation for the talk. So now I want to actually set some notation. So K for me is always going to be some algebraically closed field. And if I don't mention it, all categories are going to be assumed to be linear over this field K. T is going to be a finite tensor category. So just to remind you the definition, so of course it means we have some bilinear tensor product. We have this finiteness property, so Hom spaces are finite dimensional, and we have finitely many simples and enough projectives. We also have every object is finite length. And we have rigidity assumption, so we have every object has a left and a right dual. And then lastly, the unit object is simple. If I write underline T, then this just means the stable category of T. So just like in the last talk, this means we factored out by projective objects. This is now a monoidal triangulated category, no longer abelian. And some of these theorems, although my motivation is really coming from studying stable categories of finite tensor categories, some of these theorems I'm going to state in the generality of just an arbitrary monoidal triangulated category. So for me, throughout the talk, this will always be K. And okay, I'm not going to ever assume that there's any kind of braiding or symmetric braiding. I don't know why I wrote unless explicit. I don't think I put any explicit braidings in this talk. And I should say as a disclaimer, so I think everything in this talk that I'm going to say, I might not give the references for it after every result, but I think everything was known previously in the symmetric case in work of Paul Balmer and Balmer Favi. So these are kind of only new theorems in the non-commutative situation. Okay, and then of course throughout one is going to denote the tensor unit. Okay, so also just a few more reminders from the previous talk. So Balmer spectrum was developed originally in the symmetric case in the early 2000s. I'm going to use these natural non-commutative analogs. So a thick ideal in a monoidal triangulated category is just a full triangulated subcategory closed under direct summands and tensor products with arbitrary objects. Or if you prefer, you can think of this as just the kernel of some monoidal triangulated functor. Just like an ideal in ring theory is supposed to be kernel of a ring homomorphism. And the Balmer spectrum is just the collection of prime thick ideals. So thick ideals P, which satisfy this prime condition over all thick ideals I and J. So if I tensor J is contained in P, then one of I or J has to be contained in P. And of course, this Balmer spectrum, so it's a topological space. The closed sets are generated by what we call the Balmer supports of objects. So these are supposed to, in some sense, be analogous to the cohomological support that came out of the modular representation theory in the 80s. And so the point is you should be able to plug in an object of the category and output a closed subset of the Balmer spectrum. So here this is defined as this closed subset corresponding to an object A is just the collection of prime ideals which don't contain A. Oh, and yeah, so I should say, right, so as we saw in the last talk, there's this Balmer spectrum is kind of a formal space which is intended to parameterize the thick ideals of the category. In this case, I guess I'm assuming implicitly that this category is rigid, so we're actually parameterizing all thick ideals and not just the semi-prime ones. And the point is there's a bijection between thick ideals on one side and Thomason closed sets of the Balmer spectrum on the other, using this Balmer support map. And this is just given in the following way. So if you have a thick ideal I of K, you send this to the union of the Balmer supports over all the objects in I. Or to go the other direction, if you start with a Thomason closed subset, you assign to this the collection of all objects whose support is contained in that subset. Okay, and this is a fact that's going to be used throughout all of the results in this talk. It allows us to kind of go back and forth between the geometry in the Balmer spectrum and the category itself. So we have two guiding philosophies for how we want to approach study of the Balmer spectrum at this point. So one is that we want to treat our monoidal category like a ring, and that's evident even in just the definition of the Balmer spectrum, right? We say, oh, we know what a prime ideal of a ring is. Let's make an analogous definition on the level of the category. And the second piece of this philosophy is that categorical properties of K should really be reflected in topological geometric properties in the Balmer spectrum. And this is the point of my talk where I check my time, and if I've done a terrible job managing my time and I'm out of time and have to stop here, then I say, okay, let me just summarize the main theorems of this talk. So theorem 1, that a monoidal triangulated category behaves like a ring. And theorem 2 is that categorical properties of K are reflected in topological properties of the Balmer spectrum. Okay. But fortunately, okay, I'm not out of time, so I can actually tell you what these theorems actually say. And to give a little bit more motivation for this, so again, just to recall these results from the previous talk, given any finite tensor category, we have this particular subalgebra C bullet, the categorical center. This is some subalgebra of the cohomology ring. We define a version of support varieties relative to this algebra. And we have this conjecture that for any finite tensor category, the proj of the categorical center really identifies with the Balmer spectrum of the stable category. So the situation then that we find ourselves in is that, well, we've conjectured this kind of relationship between Balmer support and a version of cohomological support. And okay, this conjecture is, in general, we expect it to be hard to prove, although we know examples of it. And we know Carlson's Connectedness Theorem, which is a theorem about, well, that the cohomological support of an indecomposable module is connected. Maybe we need some assumptions on this, but we have this theorem on the level on the side of homological support. So the natural question is, well, is there a version of this Carlson Connectedness Theorem on the other side, on the side of the Balmer support? I mean, if our conjecture is true and these things really do coincide, then of course there has to be. So the first theorem that I want to say is, this is a theorem, of course, joined with Non and Dan. If K is any monoidal triangulated category, which is generated as a fixed subcategory by a single object, and we also need it to be the compact part of some compactly generated monoidal triangulated category. This is going to cover all of the stable categories of finite tensor categories, which I'll explain a little bit in a minute. And if this is true, then we get exactly a version of Carlson's Connectedness Theorem on the level of Balmer support. So if A is an indecomposable object in K, then the Balmer support of A is indeed connected. So most of the remainder of the talk is going to be a general outline of how we prove this theorem. And the way that we prove it is by the second theorem that appears in the title of the talk, which is a generalized Chinese remainder theorem for monoidal triangulated categories. So let me say a little bit more about this context that we're in order to explain how we prove this. So like I said, we need, in order for this theorem to work, we need K to be the compact part of some compactly generated monoidal triangulated category. So what does this mean? So an object in a triangulated category is compact as long as Hom out of that object commutes with arbitrary coproducts. So that's in particular, possibly infinite coproducts. And we say that some monoidal triangulated category K hat is compactly generated if, well, firstly, we need arbitrary set indexed coproducts. So this is not going to be a non-example of this compactly generated monoidal triangulated category would be the stable category of a finite tensor category. In that case, we don't have arbitrary set indexed coproducts. So this is kind of a bigger category than that. And of course, exactly what you expect when I say compactly generated. I want the category to be generated by the collection of compact objects. So that is, it's the smallest category which contains the compact objects if I'm allowed to take arbitrary set index coproducts and then close it as a triangulated category. And so, for example, if we take some finite dimensional Hopf algebra H, we can realize the stable category of the category of finite dimensional H modules. This sits at the compact part of the compactly generated monoidal triangulated category, which is the stable category of all H modules, so possibly infinite dimensional ones. Or more generally, if you have some finite tensor categories T, then T underlined sits as the compact part of just the stable category of the indization of T. So, so we prove this theorem in this generality of compactly generated categories, but if you prefer, our real motivation is coming from stable categories of finite tensor categories, and that's a fundamental example of this. So, okay, so what's the point? I mean, our theorem, we want to prove something just for a monoidal triangulated category K. Why do we need this K hat? Why do we need these arbitrary set indexed coproducts? Well, the point is, so here I guess I'll introduce some notation. So let me set log I to be the localizing category generated by some subcategory I. So here I just want to close it as a triangulated category, except I'm also allowed to take set indexed coproducts. Now the payoff for being in a compactly generated triangulated category is that we have access to Brown representability. This is a very general result. It's due to originally I think the triangulated version is due to Niemann. And what does this say? So here we have log I. So I here is intended to be some fixed subcategory of the compact part K. Log I is some subcategory of K hat. So we kind of automatically have this functor, just the inclusion functor, which is this I lower star, which includes log I into K hat. We also have this Verdier quotient, which is K hat quotient by log I. So here this is some formal quotient where log I becomes isomorphic to 0. So of course, coming with this Verdier quotient, we get automatically a functor J upper star, which goes from K hat to the quotient. What Brown representability says is that these functors, we can actually construct adjoints to them. So hence we get these two lower arrows, I shriek and J lower star, which kind of go the opposite directions. But these adjoint functors, I mean, these really need the arbitrary set indexed coproducts in order to be defined. And in particular, even if you start with a compact object, once you apply these adjoint functors, it might take a compact object to a non-compact object. So you can't remain within the compact part, even if that's what you want to do. And okay, using these two functors, we construct what are usually called the Ricard idempotent functors. I think these were originally produced by Ricard in the 90s. So these give us two functors that go from K hat to K hat, one by passing through log I, and one by passing through the quotient by log I. So these are Li and gamma I. And gamma I here takes value in log I. I mean, it's applying the adjoint to log I and then including back in. And Li takes values in log I perpendicular space. So objects which admit no maps from objects in log I. And the really useful part is that given any object A, we get a distinguished triangle which goes from gamma I of A to Li of A. And this is a really useful technique which allows us to, in some sense, kind of split A into, I mean, we think of gamma I of A as kind of the part of A which lives in log I, and Li of A is kind of the part which lives perpendicular to log I. Okay, so I told you the way that we're going to prove the generalized Carlson theorem is by proving a version of the Chinese remainder theorem. So let me remind you what the classical Chinese remainder theorem is. So here we have some ring R. We have some collection of pairwise coprime two-sided ideals, I1 up to In. Then we have an isomorphism that goes from R quotient by I to the product of R quotient by I sub 1 up to I sub n. Where here coprime just means that if you take any I sub I and I sub j, then they together generate the whole ring. And I should say an I here is the intersection of all of the I sub i's. Okay, so now I can tell you this generalized version of the Chinese remainder theorem for monoidal triangulated categories. So here the setup is K is some monoidal triangulated category, which is the compact part of some compactly generated monoidal triangulated category, K hat. And we have I sub 1 up to I sub n, some collection of thick ideals of K, which are pairwise coprime. Then we get equivalences of monoidal triangulated categories. So on the setting of the big category, here we do K hat quotient by the localizing subcategory of the intersection of all of the I sub i's. And this is isomorphic to the direct sum of just K hat quotient by log I sub 1, direct sum up to K hat quotient log I sub n. So this is on the non-compact level. And then by passing the compact parts of these categories, we get a decomposition of the idempotent completion of K quotient by the intersection of these ideals into a direct sum of K quotient by each ideal individually, and then idempotent complete. And here, just like for rings, coprime just means that if you take any two of these ideals, they should together generate the whole category. So let me sketch the proof of this Chinese remainder theorem. So if I and j are coprime, then one can show that Li of 1 tensor Lj of 1 is isomorphic to 0, which means that actually Lj of A is the same thing as gamma I of A for any object A. And what follows from this is that the standard Ricard triangle associated to A and associated to the ideal I actually splits for each A. So here, this gamma I of A actually lives in log I, and Li of A lives in log J. So this is how we decompose every object A into a part that lives in log I and a part that lives in log J. From this theorem, you can do the decomposition giving any two coprime ideals. And then the point is you want to extend this to arbitrary collection of coprime ideals. And this is fairly straightforward. If you have three pairwise coprime ideals, then the intersection of the first two is indeed coprime to the third, using this kind of classic lemma. And this allows us to now decompose for some arbitrary finite list of coprime ideals. And then in order to pass to the compact part, we use this is kind of a standard theorem, which is that if you take the, this should be the compact part of this. So the compact part of K hat quotient by log I is the idempotent completion of just K quotient by I. Okay, so now we have a generalized Chinese remainder theorem. So let me sketch how we then get the Carlson Connectedness Theorem once we have the Chinese remainder theorem. So here two ideals I and j are coprime if and only if the union of the supports of I and j is all of spec K. So this is of course using our classification theorem, which lets us go back and forth between thick ideals and closed subsets of the Balmer spectrum. And okay, so then 2 is that the intersection of I and j is empty if and only if the supports of I and j are disjoint. So now if we have some arbitrary, if the support of A is disconnected, then we can write it as some disjoint union of V of B union V of C for some objects of B and C. Then the Chinese remainder theorem says that we actually get a decomposition of A into Li of B direct sum with Lj of C. Okay, so with my last couple of minutes, let me give some special cases and examples. So special case of this, of course, is if the whole Balmer spectrum itself is disconnected. So if we can write spec K as a disjoint union of Zi union Z1 union Z2, And if this is some idempotent complete monoidal triangulated category K, then there exists some objects A and B with B of A equal to Z1, B of B equal to Z2. And then we have I equal to the ideal generated by A, J the ideal generated by B. Then if we set these ideals as such, then these are coprime complementary ideals. And what it follows is that K can be written as the direct sum of just the idempotent completion of K quotient I and K quotient J. And fortunately, on the level of Balmer spectra, idempotent completion doesn't affect the calculation of the Balmer spectrum. So what we have here is if the Balmer spectrum of K is disconnected, then actually you can write K as a direct sum of two triangulated categories, and the spectra of those two triangulated categories are exactly the two pieces of your spectrum, of your original spectrum. So another example, so let me come back to my second slide, which was on disconnected schemes. So here X is some disconnected scheme. K is the perfect derived category of X. Then, yeah, I don't know why I put perfect derived category because I'm just going to say something about the full derived category. So this is now using the Chinese remainder theorem. It says, okay, we can write, we can take D of X. This is isomorphic to, well, here I1 is supposed to be things which are supported on X1. I2 is things which are supported on X2. So this loc of the intersection is trivial. So we can write D of X is the same thing as D of X quotient by this localizing category generated by an intersection. And the Chinese remainder theorem says, actually, this is the same thing as D of X quotient by loc I1 plus D of X quotient by loc I2. And then this is a result of, a classic result of Thomason, is that actually this D of X quotient by loc I1 is the same thing as D of X2. And D of X quotient by loc I2 is the same thing as D of X1. So we're able to, I mean, this kind of straightforward fact that D of X decomposes as this direct sum, we can kind of recover this fact. It falls out straight from the Chinese remainder theorem as well. Okay, and then I think that the last example I want to say is, in particular, if we have K is a stable category for some finite group, we're again in a field of characteristic dividing the order of G. In this case, the big stable category, K hat, is just going to be the stable category of arbitrary modules of KG. Then we can consider the irreducible components of spec K. So spec K in this case is the same as proj of the cohomology ring. We have some irreducible components, Z1 to Zn, and we can make the definition that I is just those objects of K such that the dimension of B of A is less than R. And J are those objects of K such that each of these irreducible components is not contained in B of A. I guess I didn't write it. I think R is supposed to be the maximum of the dimensions of Z1 up to Zm. So then this Chinese remainder theorem is exactly something that was studied by Carlson, Donovan Wheeler, Benson, and Benson Krause. So they studied these categories precisely, these K mod I idempotent completion and K mod J idempotent completion in the late 90s and early 2000s. And indeed obtained that these categories are direct sums. And this does fit into the situation of the Chinese remainder theorem because each of these ideals I and J can be written as intersections of some collection of maximal ideals. And of course, any two maximal ideals are pairwise coprime. So exactly our general Chinese remainder theorem does recover these decompositions. So I think that that's all I want to say. So thanks for your time.
I just said, you do Jefferson ready,
Sorry?
Jefferson ready. You did a Chinese remainder theorem,
Mhm.
and you have many maximal ideals and what.
Yeah, yeah, exactly.
Get
Exactly right. Exactly right.
So that's the topic for